Hi, today we will be presenting the experiment 6, thin layer chromatography, and I will take part on the introduction and objectives. So first, the introduction. What is chromatography? Chromatography is a technique used to separate, identify, and quantify components in a mixture. Thin layer chromatography (TLC) is a fast, co-effective, and highly sensitive analytical tool which uses for monitoring reaction progress and purifying small compound amounts. Next, retention factor and polarity. Each separated compound appears as a distinct vertical spot with a unique retention factor RF value. Polarity indicator. Less polar compounds travel faster, which causes high RF retention factor. More polar compounds stick to the plate, which causes low RF retention factor. Factors that affecting the RF values varies with temperature, moisture, chamber saturation, and solvent parameters. And the key exception is thicker plate layers decrease the RF value because the mobile phase moves slower. Next, for the objective, first is to observe the solvent front. Second, to calculate the retention factor, RF values, to determine the purity of a sample, and lastly, to determine the effect of the solvent on TLC analysis.
So for next part is which is the material and apparatus. The material needed is the methyl red, xylenol orange, bromo green, acetone, ethyl acetate, hexane, and alcohol. The apparatus needed is the TLC slide, beaker, parafilm, micropipette, ruler, and pencil.
So I will be explaining on our results. So for our results, we will be evaluating the separation performance of six different mobile phase solvent on three specific dye solution, which is the methyl red, xylenol orange, and bromocresol green. For all the setup, the solvent front distance was tracked at 5 centimeter. So looking at our first four solvent system on this slide, which is the acetone to hexane for the ratio 3 to 2, we can observe the migration distance with methyl red recording a height migration value of 5.2 centimeter. But then when we switch to acetone and ethyl acetate in a ratio of 1 to 1, the spots migrated near the top of the plate, resulting a height calculated RF value, which is all above a 1.0. For ethyl acetate and hexane, with the ratio of 3 to 2, we could achieve a more subsequential distribution with RF values ranging from 0.54 to 0.90. Finally, the acetone and ethanol for the ratio 1 to 1 has a relatively compressed distance where both the silenol orange and also the bromochrysal green travel with the distance of 4.8 centimeter, giving them an identical RF value of 0.96. So next we have the ethyl acetate to ethanol with the ratio of 1 to 1. The dyes migrated significantly up the plate, resulting in a close RF values between 0.72 and 0.86. While for the hexane to ethanol with the ratio of 1 to 1, we can observe a slightly wider spread with the RF values ranging from 0.70 up to 0.90. So the question is, which solvent mixture gave the most complete resolution of the three dyes? Which solvent gave the porous solution? The answer is the mixture ethyl acetate to hexane with the ratio 3 to 2 gave the most complete resolution of the three dyes. Meanwhile, acetone to ethyl acetate with the ratio of 1.1 gave the porous solution from the three dyes. And below here, we can see some of the TLC plates that we did during the experiment. So some of the data we obtained is from the other group. So lastly, for our calculation part, we uses the formula RF equal distance spot travel from the origin line over solvent front distance. So a higher RF values indicate that the component has a higher affinity for the mobile phase, while a lower RF value signify a stronger adsorption to the stationary phase.
For the next part, which is discussion, thin layer chromatography, or TLC, is a method to separate components based on the polarity. There are two phases, which are stationary phase, which is the silica gel on top of the plate, and mobile phase, which is the solvent system that we mixed. So retention factor, or RF, is a distance spot traveled from origin line over the solvent front distance. It is a ratio used to identify substance based on how far they move relative to the solvent front. So in this experiment, there are three dyes that are analyzed: methyl red, bromochrysal green, and xylenol orange. There's also a mixture of all three dyes that is to be analyzed. So next are the key points, which are the solid stationary interaction. So in silica polarity, silica gel is highly polar, and polar compounds form strong hydrogen bond with the surface, which slowing the migration of the dyes by the solvent front. Next is the solid polarity. From the dyes, xylenol orange is the one that has the highest polarity, which will exhibit lower RF values as it is strongly attracted to the silica gel. So, since there are two phases, and the one that silica and solid polarity is of is the stationary phase. Next is the mobile phase. So, less polar compounds, which seemingly is methyl red, prefer the mobile phase and travel further, resulting in higher RF value. So in the experiment, to avoid further errors, there are important procedures that must be adhered to. The first one is during the preparation, after the mixtures were added, the beaker must be covered with parafilm to ensure chamber saturation, preventing solvent to evaporate to the air during development. Next one is spotting. Samples must be applied using a capillary tube, and it should not be pushed too harder to a point that it scrapes the silica gel. So, additionally, pencil markings were also used for the baseline to avoid ink interference if we use pen with the organic dyes. So, based from the analysis that was seen during the calculation, the most optimal separation is the ethyl acetate hexane with the ratio of 3 to 2, produce an even separation with evenly distributed RF values, while the poorest one is acetone to ethanol. 1-to-1 ratio due to the excessive spot spreading. Well, one of the one with the most error is the acetone and ethyl acetate 1-to-1 ratio, resulting in exceeding one value of RF, indicating that the solvent front overran the spots. So we see that the polarity influence of the mixture, where higher polarity solvent systems generally cause solutes to travel closer to the solvent front. So that is all for the discussion.
To conclude, in this experiment, thin layer chromatography (TLC) was successfully used to separate the components of the dye mixture. From this experiment, we observed that different compounds travel different distances because of polarity and solubility in the solvent system. To identify and compare the compounds, RF values were calculated. Other than that, different solvents produce different levels of separation due to the different in solvent polarity. For the post-lab question 1. Why is it important to keep the spots applied to TLC slides for chromatography as small as possible? It is important for resolution. When the solvent moves up the slide, the spot naturally spread out due to diffusion. If the spot is too large, the separated components will overlap, making it hard to measure the distance they travel. Second, why is it necessary to keep the beaker used for chromatography tightly covered with parafilm while the solvent is rising through the TLC slide? The beaker is covered with parafilm to prevent the solvent from evaporating and maintain a saturated solvent atmosphere inside the chamber. This allows the solvent to rise evenly up the TLC slide and give more consistent results. Last question. Of the solvent used, some were very polar, example acetone and ethanol, while others were very nonpolar, example hexane. Thus, the polarity of the solvent of the various solvent mixtures seem to affect the completeness of the separation of dyes. Why might this be so? Yes, the polarity of the solvent mixture affects the separation of dyes. Polar solvent can move polar dye molecule further up the TLC slide, while nonpolar solvents are better for moving nonpolar substance. A suitable solvent polarity gives better separation because the dyes move at different rates.